What specific problem does the JumpReLU say method aim to solve in the context of sparse autoencoders for language model activations?
The JumpReLU say method aims to address the trade-off between sparsity and reconstruction fidelity in sparse autoencoders (SAEs) for language model activations. Traditional training methods often struggle to balance these two objectives, as increasing sparsity typically leads to a loss in reconstruction quality. JumpReLU SAEs introduce a modified activation function that incorporates a thresholding mechanism, allowing for more effective feature selection while maintaining reconstruction accuracy. Additionally, the method employs a loss function that utilizes an L0 sparsity penalty, avoiding the pitfalls of L1 penalties that can harm fidelity. By leveraging straight-through estimators (STEs) to estimate gradients for training, JumpReLU SAEs enhance the training efficiency and performance of SAEs compared to existing architectures like gated and top-K SAEs.
How does the JumpReLU say method work? Illustrate its steps from encoding to decoding, focusing on the modifications introduced in the activation function and loss formulation.
The JumpReLU say method operates by encoding language model activations through a modified activation function and a specific loss formulation. First, it employs a JumpReLU activation function, which replaces the traditional ReLU function. This new function zeroes out pre-activations below a positive threshold, allowing for a more controlled selection of active features. The encoding process generates a sparse, non-negative vector of feature magnitudes, which are then used to reconstruct the original activations through a decoder function. The loss function used for training JumpReLU SAEs is a weighted sum of an L2 reconstruction error and an L0 sparsity penalty, which is advantageous as it avoids the limitations of L1 penalties that can penalize feature magnitudes and affect reconstruction fidelity. To address the challenge of training with a piecewise constant loss function that provides no gradient for the threshold parameters, the method utilizes straight-through estimators (STEs) to estimate the gradient of the expected loss, enabling standard gradient-based training.
What are the practical advantages of using the JumpReLU activation compared to traditional ReLU and other methods like gated and top-K SAEs?
The JumpReLU activation function offers several practical advantages over traditional ReLU and other methods like gated and top-K SAEs. Firstly, JumpReLU SAEs consistently provide more faithful reconstructions than gated SAEs at any given level of sparsity, and they often outperform top-K SAEs as well. Additionally, JumpReLU SAEs require only a single forward and backward pass during training, making them more efficient compared to top-K SAEs, which necessitate a partial sort. Furthermore, unlike gated SAEs, which rely on an L1 sparsity penalty that can harm reconstruction fidelity, JumpReLU SAEs utilize a L0 sparsity penalty, avoiding the limitations associated with L1 penalties. Overall, these features make JumpReLU SAEs a mild improvement over existing SAE training methodologies, balancing efficiency and reconstruction quality effectively.
Can you explain how the performance of JumpReLU SAEs was validated in the experiments? What datasets and metrics were utilized to compare its effectiveness?
The performance of JumpReLU SAEs was validated through experiments that compared them against gated and top-K SAEs using activations from the GEMMA 2.9b model. Specifically, the SAEs were trained on residual stream, attention output and MLP output activations at layers 9, 20, and 31, utilizing a dataset comprising 8 billion tokens. The effectiveness of the models was assessed using two primary metrics: the mean L0 norm of feature activations to measure sparsity and delta LM loss to evaluate reconstruction fidelity. The results indicated that JumpReLU SAEs consistently provided similar or better fidelity at a given level of sparsity compared to the other SAE architectures, as illustrated in the figures presented in the paper. Additionally, interpretability studies were conducted to assess the quality of the features learned by JumpReLU SAEs, further validating their performance.
What key results were reported regarding the performance of JumpReLU SAEs, especially in terms of sparsity and reconstruction fidelity relative to gated and top-K SAEs?
The key results reported indicate that JumpReLU SAEs consistently provide more faithful reconstructions than gated SAEs at any given level of sparsity. Additionally, JumpReLU SAEs offer reconstructions that are at least as good as and often slightly better than those produced by top-K SAEs. In terms of efficiency, JumpReLU SAEs require only a single forward and backward pass during training, unlike top-K SAEs, which necessitate a partial sort, making JumpReLU SAEs more efficient to train. Furthermore, while JumpReLU SAEs exhibit a tendency for more high-frequency features compared to gated SAEs, they maintain a low proportion of such features overall with fewer than 0.06% activating more than 10% of the time. Overall, these findings suggest that JumpReLU SAEs represent a mild improvement over existing SAE training methodologies in balancing sparsity and reconstruction fidelity.
What limitations or challenges does the JumpReLU SAE method encounter, and what future work do the authors suggest to address these issues?
The JumpReLU SAE method encounters a few limitations, primarily related to the evaluations presented in the paper, which focus on training downstream tasks like circuit analysis or model control, rather than directly assessing the performance of the JumpReLU SAEs in those contexts. Additionally, while JumpReLU SAEs show improvements in reconstruction fidelity and interpretability, the authors acknowledge that they still have relatively more very high-frequency features compared to gated SAEs, which may affect interpretability. To address these issues, the authors suggest that further work is needed to enhance the performance of JumpReLU SAEs in practical applications and to mitigate the limitations associated with high-frequency features. They express hope that future research can refine these aspects, potentially leading to more effective implementations of JumpReLU SAEs in real-world tasks.